Hi, Damian. So by the way, what's the IDIAP mean? So it's a word or it's just a kind of a logo? So how to pronounce it?
Yeah, you say IDIAP.
IDIAP. Okay.
Yeah.
IDIAP. Okay. Good.
When the institute was created, it was an acronym, but it was something in French, so they basically dropped the acronym. I forgot what it was, but it meant something originally. Now it just became a word by itself.
Okay. IDIAP. Okay. Sounds
yeah.
good.
Yeah, it's good. Yeah. Yeah.
So you also so you have been also working with Xiaodong He and also Peter Anderson previously, right? So
right. Yeah.
So many papers together.
Yeah, indeed. Yeah. Common.
Cool. Yeah. So I think how about we first getting started, and then so we have so 20 people here, and usually during the talk, more people will join us. So let's begin. So maybe I will first introduce today's speaker. Today's speaker is Dr. Damian Tenney, who is a research scientist heading the machine learning group at the IDEAMP Research Institute in Switzerland. He is best known for his work at the intersection of computer vision, machine learning, and also natural language processing. In particular, he was part of the team that won the challenge on VQA at the CVPR 2017. His work has introduced the famous bottom-up, top-down visual feature that has been widely used in almost every architecture for vision and language nowadays. More broadly, he is interested in building a robust machine learning model that can truly understand the world around us. He has previously been affiliated with the University of Adelaide in Australia, CMU, the University of Bath, the University of Innsbruck, and the University of Leeds in Belgium, where he is originally from. And for this virtual visit, he will be joining us remotely from the IDEAMP Research Institute in the beautiful Swiss Alps. So without further delay, I will hand over the time to Daniel.
Yeah, thank you very much. Thanks for having me again. Yeah, so I'm really excited to be with you today. With you virtually. And so in this talk, I'm going to share some reflections about the state of the art in vision and language, and in particular about the limitations for visual question answering. Since I could not visit in person today, I will just take the opportunity to share with you the view that we have from the office where I am here in Switzerland. So I am with the IDEAP Research Institute. It's an institute where we do research in AI broadly. And I moved here a few months ago, and I'm now heading the machine learning group here. So the institute is very active in NLP, in speech processing, also in robotics. If you are interested in visiting or even looking for a new position, please get in touch with me. We have a lot of beautiful things to see around here. So I want to start this talk by reminding us why visual question answering is such an exciting task. I think that's because it's a very general but also a very complex task. We all know this example with the banana from a well-known VQA dataset. And I think the complexity really becomes clear when you look for examples in the training set that are relevant for answering this specific question. Even though you can find examples about bananas and you can find examples about mustaches, it's clear that answering this question requires much more than just interpolating between training examples. The key capability here that is required can be summarized as out-of-distribution generalization. So this means combining learned concepts and reasoning mechanisms beyond training distribution, beyond what was demonstrated by the training examples. And this is a fundamental research topic in machine learning, but it's far from solved, and most research on the topic still struggles with toy data like colored MNIST digits. So why is this difficult? That's because the principle of empirical risk minimization that we use most of the time is really about learning by association. So we learn correlations between examples and labels in a training set. And we can see the limits of this approach with just a simple example of image recognition. Let's say that we want to train, let's say, a bird detector. So first we collect some images about, images of birds. And in natural images, it's very likely that birds will appear on backgrounds of blue skies and tree branches, like these ones. And the problem is that you also want to recognize birds in different scenes, like a bird in a parking lot. But the model is probably going to learn this very strong correlation between the bird label and the blue sky, which is useless in the parking lot, obviously. So if the model relies on these correlations to recognize birds, it just won't work on those different examples. So it's important to make a distinction here between the classical in-domain generalization and the strong out-of-domain generalization. So the former is mostly about filling the gaps, very loosely, the gaps between training examples. And it's generally agreed, I think, that there are some general, almost universal biases that can help here, like some kind of smoothness prior on the classification function. And in this case, more data also always helps. So in fact, in the limit of infinite data, the in-domain generalization is solved. But the out-of-domain generalization is different. So here we need to distinguish which features are robust ones and which features are just spuriously correlated with the labels. So in our examples of the birds, we could say that the shape of the bird is maybe a robust feature, whereas the background is spurious. So here, the key thing is that you need additional knowledge that has to be task specific. And to make that really clear, we could say in this data that the label is not called bird, but the label could be renamed, say, sunny day and tree branches. So just renaming the label, so using the same data, it would actually become the right thing to do to rely on the background now. So this shows that how to generalize out of distribution is often not fully specified by the data that we have. So it means that getting more examples, so more of the same biased data, does not help. And the thesis of this talk is that the complex tasks like VQA require something like that. They require stepping beyond the framework of classical statistical learning. So in this talk, I'm gonna first review some principles from causal reasoning that I find useful to formalize what we can do beyond this learning by association. And then we'll see some implications for the evaluation of models and then for the learning of better models. So if you wonder why causality matters, remember that when we say that variable x causes y, here it only means that intervening on x affects y. So that is setting x to a specific value has an effect on y. So just make that explicit with a simple task. Let's say we have images of cars and we want to predict the top speed of the car. So let's say we collect some data, say from Wikipedia. So we have images and we get the annotations of the top speed of each image. So that's our training data. And then we train a machine learning model on this data. So with a standard statistical model, you learn correlations. And in this case, you notice that we have a lot of pretty nice red Italian cars. And these also happen to be pretty fast. So it's likely that the model will learn this correlation and basically learn that red means fast. So obviously this is true only for data from this particular distribution. And obviously we know that there is no causal relation between the color and the speed. So the idea of a causal model is that we encode the effect of interventions. So that is what would happen to the speed of the car if we were to repaint it. So obviously it's not going to get any faster. So with a causal model, we can make predictions now about conditions that were not in the training data. And that's basically the definition of out-of-distribution generalization. So in these two types of models, statistical and causal, we learn very different mathematical objects. And what is important to notice is that for the statistical model, using more data, so that is more of the same data, does not turn it into a causal model. So if you get more images of red Ferraris, that's not going to help understand that the relations between color and speed is only spurious. So let's get back to VQA. And the view that I like to take here is to compare on one side the real world and on the other side the model that we learn. So in the real world, we have a set of mechanisms that produce the data that we observe, our training data. And the causal structure of these mechanisms matter because that's what defines which features are correlated with one another and which of these correlations are spurious or robust. So we call these mechanisms the data generating process. And in VQA, that's basically the human annotator. So someone who takes a question and an image as input and then identifies relevant visual information and then use that to give an answer. Now, on the other side, in a learned model, we basically want to mimic this process. And the inference of a model that's been trained also has a causal structure in the sense that it also takes inputs that lead eventually to an answer. But the structure is not necessarily the same as in the real world. For example, we can draw the causal structure of a bad model that doesn't use the image at all and only guesses the answer directly from the question. Or we could here I represented a model that doesn't have an explicit attention mechanism. But an important property of the causal model of the world on the left side, an important property is that its structure implies a factorization of the joint distribution of the variables. So this factorization is a special one in which the factors correspond to independent causal mechanisms. So these mechanisms are guaranteed to transfer out of distribution. That means that's the mechanism that we want to learn. So we don't care about, say, the marginal distribution of images, for example, but the mechanism that identifies the relevant visual information and the mechanism that goes from there to the correct answer, that's the bits that we want to learn that will make the model generalize in novel situations. So to learn a robust model, we basically want to mirror some of the causal structure and mechanisms from the real world into the learned model. So why is this hard? And the answer is that the information that we need is often absent from the data sets that we use. So typically, we have a set of ID examples, or training examples, and these are basically samples from the joint distribution. And it's actually known that from this, we cannot recover the causal structure of the data generating process. So by taking ID samples from the joint distribution, you lose the information about the causal structure. So this means that we need to bring additional information and information that has to be task specific. So we sometimes do this, for example, with specific architecture, but like designing attention models. This actually can be seen as a way to inject some knowledge about the true causal structure of the task. And the general takeaway here is that with just a standard dataset, we don't have enough information for OOD generalization. We need to bring something else to the table. So I will come back later to the learning of models. And first, I want to talk a little bit about the evaluation of models. So in evaluation, we want to know basically whether a VQA model can answer arbitrary questions about novel and unusual scenes. And a classical test set measures the in-domain generalization, so with questions from the same distribution as the training set. And that's not sufficient because it doesn't say whether the model is merely doing maybe shortcut learning, like guessing answers using dataset biases. So I think in VQA, we have made a lot of progress already in coming up with better evaluation strategies and better benchmarks. And so I mentioned a few benchmarks like VQA V2, VQA CP, GQA OOD. So all of these are improvements over the standard classical simple test set. So I think that that's a great thing. And I will show you that all these ideas from those datasets can be formalized and actually justify with causal principle very effectively. So a useful framework to think about this is called the causal hierarchy, introduced by Judy Appel. So this hierarchy defines 3 types of queries that one can make to a model. So these 3 types of queries are increasing in difficulty. The first level is the association in the bottom here. So this level is basically where we are kind of stuck with most of machine learning today. And the other levels, the interventions and counterfactuals, these are the ones that are relevant for causal reasoning. And so I will show you that these 3 levels can be matched with different evaluation settings that people have come up for VQA. The first level, the association, is the classical test set. So test set from the same distribution as the training data. So we've seen that this is pretty limited already. More interestingly, the second level, the intervention, that corresponds to dataset like VQA-CP. That's datasets where we have a different distribution between the training and the test set. And we can interpret this shift in distribution as an intervention on some variables in the data generating process. And so it's in this sense of an intervention that these datasets can be seen as level 2 interventional queries. And then the third level, called counterfactuals, that can be matched with datasets of counterfactual examples that have been proposed in a few recent papers. So many of you probably know about this. So the idea is that you have test questions that are actually pairs of questions. So in those pairs, they are very similar, but with a slight difference. The difference can be in the question, like a different word, or in the image, like an object that has been masked or painted in the image. And so those pairs of questions basically probe the model very close to the desired decision boundary. So typically those pairs of example have a different answer. The small difference make the correct answer different. And so since we can match this type of dataset with level 3, this means that this is indeed the most challenging of all types of evaluation. So that's because we know that the 3 levels are strictly increasing in difficulty. So each level requires strictly more causal information. And so overall, this analysis is useful because it shows that some benchmarks are indeed better than others in the sense that they test the models for better causal reasoning. And so you can use this this hierarchy, this analysis to also come up with even more difficult evaluation ideas. For example, we could imagine for VQA a setting where you would feed a model with question, image, and correct answer. I don't think that's been proposed so far. So you would give the question, image, and correct answer to the model, and then ask the model to generate an image. So generate an alternative image to support a different answer. So this would be extremely difficult because that would require, well, it would basically test the model for what it thinks would be the required visual evidence for an alternative answer. So this is even closer to the definition of counterfactuals of standard causal reasoning.
Hi, Dan. So can I have a question here?
Please, yeah.
Yeah, so I think here you have a good example about, so in the VQA field, so what's the data set corresponding to intervention and the counterfactual, right? And but then in reality, it seems many of the papers are still targeting at the association. For example, the VQA leaderboard. And every time when we think the performance cannot be pushed further, but every year in the VQA challenge, there will be an even higher number. So what do you think this kind of progress mean so from your perspective? And so what do you think so even for the VQA leaderboard, it's kind of already achieving the human parity, right? So how do you understand so this kind of progress?
Yeah, that's a very good question, and I've been very critical about the use, the continuing use of VQA V2 as a benchmark, because I think this is really giving the wrong incentive. So getting better numbers on data sets of basically the level 1, this is not improving things in the direction that we want. So I think it's pretty clear, it's been discussed even in the VQA workshop this year, that the accuracy that people are getting on this dataset, about 80% accuracy now, that looks like human accuracy, doesn't tell at all how fragile and basically how bad the models still are. So I think everybody knows that the dataset is not measuring what we really care about. So I think we have a lot of better data sets, and I would love to see the challenges using those better data sets instead of trying to push the numbers on a metric that is really not measuring what we care about.
Yeah, thank you.
All right, so I'll go on. Feel free to interrupt at any time if others have questions. So now that we talked about the evaluation, I'm gonna see some implications of causal principles for the learning of better models. So I'm gonna stick with the causal hierarchy for one more slide. An important property of this hierarchy is that a model capable of a given level requires information relevant to this level or a level above it. So this is really another way of saying that the levels are indeed increasing in difficulty. So you need more information for each level. So this also implies that we cannot learn a model capable of causal reasoning, that is level 2 and 3. We cannot achieve that only from data from level 1, the observational data. But that's usually the kind of data, the only kind of data that we have in our datasets. So we know that something is missing to learn models capable of level 2 and 3. So concretely, what does this data look like? So at level 1, as I said, that's your typical datasets of RID examples, nothing special here. At level 2, that's the data that we would get after an intervention. So after an action on the world that modifies the training distribution. And in practice, we could get multiple sets of images. If we have like an image recognition task, multiple set of images from, say, different parts of the world, or images acquired in different lighting conditions, or data that maybe was annotated by different sets of annotators. So it's the idea of having multiple sets of data that have arisen from a specific intervention. You might not know what the intervention is, but the fact that there is some change in the data generating process between those sets is bringing information. If you remix all those data sets together, you just reshuffle everything, you lose this information. But by having multiple subsets and knowing that there is a change in distribution between those subsets, that's where the extra information lies. And then at level 3, that's counterfactual examples, and that's just like the examples that we saw for the evaluation. So typically pairs of examples that are very similar, but with just a slight difference and typically a different label. So if we can get this kind of example for trading, then these carry a lot of information, and they carry information that we cannot get from other types of data. So this data is more expensive to acquire, more difficult to acquire, but they bring additional different training signal. And now we'll show that with we can better understand and explain some successful techniques from a causal perspective. There's going to be methods that basically use this kind of additional training signals and that improve generalization. So we go through 3 existing methods, and the first one is simply data augmentation. So as you all know, this is about generating additional training examples with hard-coded transformations that preserve the label. So you all know that, but what's interesting is taking a causal view. And here, well, let's say with images, we can formalize the data generating process with something that looks like the graph here. So this graph shows that images are made of both spurious and reliable features. And they are both correlated with the labels because there's a hidden confounder here, noted C. And this confounder is not observed. And we also don't know specifically which parts of the image correspond to spurious features and which ones correspond to reliable features. And we want a model that generalizes out of distribution. That means a model that uses only the reliable features such that it is robust against changes in the confounder. So from what we've seen before, we know that this cannot be learned only from examples from the joint distribution over X and Y. However, it could be done with information at level 2, like data obtained after interventions, like I said. And this is precisely what data augmentation does. So data augmentations basically simulates interventions by modifying the images such that only the spurious features are modified. So for example, let's take data augmentation that applies geometric transformations on images. This is essentially intervening on the extrinsic parameters of the camera. Or let's say with VQA questions, if we augment the questions with rephrasings, we are basically intervening on the writing style of the annotator. So now we have samples from a modified distribution that is the outcome of an intervention. And we know that this carries information about the causal mechanisms now that we didn't have before. So it's no surprise that data augmentation does indeed improve generalization. So what did we learn here? What is this causal view useful for? Well, an important implication is that the root source of the improvement is really in the specification of the transformations over X and Y that are valid for the data generating process of the task. So this means that it has to be task specific. So there's no hope of finding a universal data augmentation because it has to be tailored to the data generating process of the task. So you have to bring some information about the task here. It's something that we probably had an intuition for, but I think the causal perspective allows to formalize this more precisely. Now, another technique that we proposed last year for VQA, we call that unshuffling data. So this is basically recovering non-ID subsets of the training data. So the motivation here started from existing work on domain generalization. So that's for image recognition. So in this past work, what people do is to learn from data collected in multiple conditions. So typically you have training examples for each class in multiple domains like photographs, sketches, paintings, and so on. So you have multiple subsets of training data that are from a different domain. So our method showed that we can recover this kind of informative clusters from an existing standard dataset. So we split the training set into what we call multiple training environments. So that's just multiple subsets. And to do that, we need some task knowledge. So we apply that for to VQA in this case. But yeah, the key thing is that you need some knowledge about the task and some side annotations to do the clustering on. So in practice, we apply that to VQA and we use the question type and the answer to do the clustering on. And so from a causal point of view, this is, again, simulating interventions on the data generating process. So we can formalize this precisely. I'm not going to go through the detail here. Maybe I'll just leave it here and feel free to ask questions later. But the takeaway is, again, that you can get information from level 2, which helps with generalization. And this information is something that we have with this method that we didn't have in the original aggregated data set. So by recovering those different subsets, so it's the same data, but we cover some subsets that are not arbitrary, we have some more information in there. And again, this extra information doesn't come for free. And here, the root source of the improvement is really in the choice of the clustering condition that we use to recover the subsets. So it means that you have to bring some task-specific knowledge at some point again. So there's no free lunch. And now the last technique that I want to mention is about using counterfactual examples as training data. So this was a paper that we had at ECCV last year, where the method was applied to VQA, but also on NLP and other vision tasks. So the method really shows how to get information from level 3. And the counterfactual data consists of those pairs of examples that we have mentioned before. So they are very similar, but with a different label. And there are multiple ways to get this kind of data. For example, with language data like those movie reviews here, those were obtained from annotators. So the annotators were explicitly asked to edit some existing examples to flip the label. So the annotators were asked to change as few words as possible in the movie review to flip the label from negative to positive or vice versa. That's one way. And another way to get this kind of data semi-automatically is to use heuristics and side annotations. For example, for some vision tasks, also for VQA, you could mask objects or use existing annotations like human attention to in-paint regions that are known to be relevant for each question. So you get these pairs of examples relatively cheaply, but you still need some additional annotations or some additional information. So previous work had already used this kind of data for training, but only as additional data. So just like some data augmentation, basically. And so it was shown already that for the same amount of data, examples of this type are more effective for improving generalization than the same amount of standard data. So this was prior work. And what we realized from the causal perspective is that the level 3 information is really contained in the relations across the pairs, so not in the examples themselves. And that motivated us to design a new loss, a loss that exploits the relations between the pairs of examples. So what we do is first to compute the vector differences in feature space across every pair. And then we use these vectors to align the gradient of the classifier to make the decision boundary orthogonal to this vector. So with this additional loss, we got clear improvements in generalization across the datasets in a zero-shot transfer setting. And so we got improvements in VQA, but also on NLP and other vision tasks. And so what's really interesting here is that we were using information that was in the dataset and that was just not being used before because there was no training mechanism to really make use of this data, well, this information that was there and was just discarded before. So now I want to give some takeaways. I think the main message of this talk is that there are some limits to what can be learned from a set of ID examples. It doesn't matter how many you have. And I find the causal perspective useful to understand the limits of what can be learned in a given training condition. So I see causal reasoning as helpful here, a bit like information theory in the sense that it sets hard limits on what you can do with some given resources. And the second message of the talk is that if you learn something about the causal structure and mechanisms of the world, then you can do a lot more. So the principle of causal reasoning do not really tell you how to design or learn better models, but at the very least, they can point at directions where to find the information that was missing before. And going forward, I like to think that we could shift our focus from building better models to rather building better training environments. So that is thinking about how to provide those training signals that are missing from the datasets that we use today. So in this talk, we have seen some existing techniques that do this already, this kind of using additional information and with different types of data or side annotations. And sometimes these annotations are already present in data sets that we have, and the data, well, the signal is just not being used at the moment. So I think there are probably other cases like that. For example, in some data sets, you can find information about annotator identity that's almost never used. So you could use that, for example, to cluster the data into different subgroups of annotators. That might give you some useful kind of weak supervision there. Or you can think about using data from non-stationary sources. So in this case, you have some distribution shifts over time. And this, again, could be used as a form of supervision. So there are probably a lot of opportunities like that of signals that are available, but just not being used. And not taking a high-level view of what's been done and maybe the road ahead here is that we can draw parallels between machine learning and causal reasoning. So in machine learning, we've moved from good old-fashioned AI to deep learning, and we can now handle raw high-dimensional data. And in classical causal inference, there are a lot of techniques that exist that are suitable for discrete and predefined variables, like the kind of graph that I've included at some slides earlier. But these kind of methods are obviously not suitable for the high dimensional data that we want to use, like images and natural language. So the next step is what some people have called causal representation learning. And this is basically discovering latent causal variables and their structure jointly. So I think this will eventually emerge probably from ideas both in deep learning and ideas in causal reasoning. So those ideas might already exist separately and they will need to be merged in some ways. So I think there are a lot of exciting opportunities here, and I hope this inspired you to maybe pursue in this direction and maybe help build models that generalize better. Thanks.
So thank you, Damien. So for the great talk. Any question from the audience?
Here I have a question. Here, Damien, thank you for visiting us. This is Pengchuan Zhang from MSR. So, in fact, causal representation learning is indeed kind of very important. There are typically two approaches to, at least as far as I see, there are two approaches to achieve this. One is kind of many academic people are trying to design kind of new loss functions like environment risk minimization. There's kind of some other kind of loss functions to enforce causal or kind of representation learning. But there's another way to do that, which is as you said, collecting more data, because those kind of information really relies on the data. And also collect data means that maybe we carefully connect the paired data you mentioned before, the counterfactual you mentioned before, or I just blindly connect more data, web scale data. I hope that those web scale data can contain the kind of counterfactual data you want, and finally just train with this kind of large scale web scale data. I want to know that kind of which approach you think that will kind of faster getting the goal of learning more generalizable machine learning models. Will this lead to kind of a competition of kind of larger and larger models, larger and larger data sets, and finally academic people really cannot really follow with this large models and this large data sets?
So I think the large scale, so what we need is not, well, more data can help, but what we are really missing is other types of data, so different kind of data. So for example, the counterfactual examples, you say that you might find those in web scale data. You would only find that if you design your collection process to actually recover those pairs of examples. So like I said, the extra information that we are missing is not in the additional examples, but it's in the pairing of examples of those counterfactuals. And I think there's no dichotomy between the more data and other loss functions. So things like IRM and those kind of causally motivated approaches, if you think closely about them, they are using those different kind of signals. So IRM is using data from multiple training environments. Yeah. So that's basically what I showed. So information from level 2, so data that had been collected with different conditions.
But my question is that, is it possible that we do not need to do this very careful data selection process? We just kind of bluntly enlarge our data sets larger and larger, do a very coarse level selection, like just define rules that, okay, I will connect data from another domain, but I do not carefully kind of construct pairs, do very fine-grained annotation. So just hope that, okay, with minimal effort of data connection, then it's okay. I think the speaker dropped off.
Yeah, so I think it's due to some. No, I think it's due to some technical reason. Maybe we wait for 1 minute. Oh yeah, she's coming back.
Hi, sorry, I had a small connection issue.
Yeah, never mind. So it's just I think I finished my question. It's really just kind of the data collecting effort maybe can be reduced and maybe can be compensated by large data sets.
Yeah. Yeah. I think it's an interesting question. So you could replace some of the, so like I said, we are missing some training signals. So you can replace those signals by the proper assumptions about the causal structure of the world. So that's something you can inject, for example, with the right architectures. And so I guess it's still an open question here. How much the combination of the right inductive biases and those priors with enormous amount of data, how far we can get with that. So I think I see a bit of hope with the web scale data of improving generalization to a point that is extremely satisfactory, because we are covering such well, we are basically covering the long tail very far, and we are basically covering a distribution that is not biased in any way. So if you think about, say, ImageNet, the way the dataset has been collected and annotated imply that there are some selection biases. But if you get information from the web, and you can basically get all kinds of photographs, then you get much closer to what is a natural distribution of the world.
Yeah, exactly. So this is also sometimes when we work on causal problems, this is also frustrating because, for example, one dataset ObjectNet, which is designed to to test this kind of generalization ability, causal kind of feature learning ability, but currently the best model, I think, until last year, still, for example, BIT, which is training with kind of web scale data, but the model architecture, the loss function is still the same with the traditional one.
Yeah, right. Yeah.
Yeah, thanks. Yeah.
Good questions. Thanks.
Oh, hi. Can I ask a question?
Yeah, please. Thanks.
Oh, so one shortcoming of the current data sets for VQA, I see that is that the answers all seems to be fixed, right? So the answers is fixed set of answers. It's quite artificial and make it easy for people to maybe to overtrain or something, right? If you make it harder to train a model that's generalizable. Typically in real world, that's rare. That's very rare, right? For example, if you ask a person, what is the person doing? You can say, oh, the person is eating. Or you can say the person is cutting the meat, or the person is having dinner with the friends together. Or the person is talking while the person is eating, right? So you could have many answers, and all the answers are actually correct. So, but currently the data sets you have the answer exactly the same one. Otherwise, you're wrong. But that is quite artificial. I just wonder if you can, have a comment on that.
Yeah, I totally agree. I think that's both for I can think about that for both the evaluation and the training, with an evaluation about where we had multiple correct answers, then we could probably better evaluate whether the model is doing something sensible. And if we had those annotations for training, we'd probably get much closer. So if you, well, those who have worked with VQA models know that sometimes a model give an answer that had like a synonym of the correct answer, or maybe just singular instead of a plural form, and then it gets counted as a wrong answer, whereas it's actually correct. It's just not the right one in the dataset. So yeah, I guess that would help both a better evaluation and also training better models if that's in the training data. Yeah.
Okay, thank you.
So I don't have really a question, but more of kind of like a discussion topic here that I'd like to bring up and just get your thoughts on. So we have, both the concepts of causal inference, so having some type of structured knowledge and then being able to make some predictions from that structured knowledge. And then we have correlation coming from observations, right? And typically in the human mind, you can look at particular kinds of environments where take physics, for example, right? You make some observations about the world. From the correlations of the observations you make some kind of like causal structured knowledge to help you explain what you're observing in these correlations, right? And then you can kind of like tweak that causal model that you have to make a new prediction and then test it, make sure that the correlations that you observe align with your causal models, right? I kind of feel like with all the benchmarks and all the data sets we use to train right now, you're limited to a fixed environment. Where really, like, these two things are kind of like two sides of the same coin: the correlation and the causality, right? They inform one another and they test one another. And what happens with people is that you constantly flip back and forth, right? You observe something, you learn something, you say, okay, well, maybe I can build this structured model to help explain what's going on, and let me try changing the model and see if what the model predicts I actually get in reality. And it's kind of like the cycle, right? I guess my open-ended question would be, how do we develop benchmarks that allow you to test a system that works with that cycle?
Yeah, it's a very good point. So that's basically the gold standard for causal discovery. That's the randomized control trial. So that's just acting on the world and seeing what the outcome is. If you can do that, that's the best way to discover the causal structure. I think there's no free lunch here, in the sense that if you want to interact with the world, or you want to let the model interact with the world, you need access, like a direct access to the world. And people are kind of trying to do that with simulators. So there's a community building, well, a part of the VQA community actually moving to 3D simulators of very complex environments, like households, basically kitchens and all that, where you can, well, the agent can move stuff and navigate the environment, push objects around, all that. So I'm saying there's no free lunch, because you have to basically reproduce the world in the simulator. So the knowledge, you basically have to reconstruct the world in a simulator.
Yeah, interesting. I guess that's sort of like the answer. If you can build these toy environments, you can have an agent kind of like play in an experiment. Then I guess if your simulation gets good enough, you can let it play outside of the simulation at some point.
Yeah, so I can see those simulators being useful, kind of the meta learning thing, where the agent would learn strategies for causal discovery, but then you would still need to, just like you said, let him loose in the real environment to apply those strategies to build its own model of the real environment. Otherwise, it's only going to learn about the kind of stuff that are in the simulator.
Yeah. Right. Interesting. Yeah, cool topics. Thanks for your thoughts.
Yeah, thanks.
So I also have a related question. So regarding to Pengchuan's comments just now. So for example, when we do large scale, the large scale pre-training, right? So which is very popular in the current. So no matter in image, no matter in NLP or vision language, so pre-training is very just popular, and this kind of pre-training is kind of doing. Kind of have the effect of doing the intervention, right? Although we are not carefully designed, so as just Pengchuan mentioned, although we are not carefully designed the counterfactual path, but then maybe as your data becomes larger and larger, you may, from the noisy data, you may see some effects of the counterfactual reasoning. So, and then, although this is so because if you want to do carefully labeling of the counterfactual examples, maybe this is just too costly and not easy to scale up. But then from the other side, it's indeed not ideal. So from your perspective, did you see any opportunity that we can bring the causal principle into the pre-training, rather than only focusing, for example, on the downstream tasks such as VQA? And then if this is possible, how can we do that? Or just not that easy to be possible? Yeah, that's my question.
Yeah, so I think think about the causal point of view helps in understanding what is missing from just a data set that may be very large. So tie that with the kind of unsupervised learning that we see working really well nowadays, the contrastive objectives that work really well, these can be interpreted as a form of counterfactual learning from counterfactuals. And here, the important piece of making this work is how you choose the positive and negative examples. So we have, well, typically we have heuristics to select those. And so what you realize from the causal perspective is that that's really the key to make this work. If you select arbitrary examples, pairs of examples, then it's not going to work. So in practice, we have seen that. So you need to choose them carefully. But the causal perspective really shows that clearly that's where the additional information is coming from. Does that bring a bit of information to your question?
Indeed, I want to comment here. Indeed, kind of the key part of this kind of contextual learning is the choose of positive and negative pairs. And I want to could you share your kind of experience on kind of bad construction of these pairs will not result in good kind of good generalization ability, because typically we kind of, at least I believe that this kind of large scale contraction learning will be very robust to data noises. So when we look at our kind of webly connected data, the kind of image text pair are very noisy, but still we can get quite reasonable results, which already shows that okay, this kind of training is robust to kind of training noises. Which means that maybe the pair is not good. It still works well.
Mm-hmm. Yeah, I guess you have much more experience than I do, so yeah, I would trust your experience more than mine.
But I want to kind of hear your kind of experience, kind of what kind of things that you found it's sensitive or fragile.
Yeah, I don't have direct practical experience to report here. Yeah.
Okay, thanks. Yeah.
So yeah, I guess what to follow up on that. That's you can replace, so the additional signal that you want to bring, you can replace that in some cases with the right heuristics. But the heuristics have to be designed properly for the task, or at least the kind of data that you have.
Mm-hmm.
Yeah, no, it's a very general comment that does not have a direct applicability, but yeah, that's all I can say, I guess.
Yeah, thank you. So any more questions? So I think if no, so we are also right on time, and let's thank you our speaker again, and then that will be the end of the talk. Yeah, thank you.
Great. Yeah, thank you very much.
Thank you.
Bye bye.
Thank you. Bye bye.
Thank you.
Thank you.